Hi, thank you very much for your interest. We are going to talk about spin wave computing, a very particular implementation of this technology, which I think has a lot of promise. There are a lot of information in these three articles. They contain many examples and include information on dimensions used, material parameters, so on, so on, so on. So if you have any questions of this kind, please consult one of those. The general interest in alternatives to CMOS and spin wave computing in particular is driven today by the fact that in the past 2 decades we saw a shift from general interest by all chip producers being captivated by general devices that had a lot of precision, that were capable of dealing with any possible task, were not specialized, and today, instead, we see the growth that is mostly concentrated in the AI, concentrated in the video industry, with very specialized algorithms, algorithms that do not deal with very precise data. It's a real world data, so real representation of 3, 4, 5 bits is often sufficient. But what becomes the gating factor today is power consumed. So even with the current technology, we can make very impressive systems, a very impressive AI cognitive ability, but the power consumed is astronomical, which makes it uncompetitive to, well, first and foremost, humans. So the idea is how we can replace CMOS computing in specialized tasks. And the two most famous candidates for this optical and quantum computing. I mean, I'm going to talk a lot about quantum computing. It's a very, very specialized and unusual field, but to run much, to read a bit ahead, actually, both optical computing and spin wave computing is capable of implementing certain quantum algorithms. But optical computing is what actually inspired the technology we're going to talk about in this presentation. In particular, there are many schemes proposed where you have photonic crystals, so you have an array of dots with different optical properties, and this array can do, for example, phase inversion or beam splitting or join the beams together. And with beams, with an inverter and joining the beams, you can make actually a logical element. Now, there are hundreds of articles, there are many, many startups, but there's still no commercially successful chips, and I think there are very intrinsic issues with the technology that prevent it from being commercially successful. First and foremost, you deal with light waves, so basically 1 micron is your wavelength, and your logic element therefore has to be larger than this. It has to be, let's say, 5 microns. And it does exactly the same job as done by a single transistor, which is 30 nanometers in size. So you immediately lose 100 on your linear density, and it can be even 10,000 when you kind of talk about your area density. So colossal difference. You are not going to have a chip with a lot of elements, and the problem is, even if you do make a chip with 1,000 elements, it's going to be quite expensive because you need to manufacture each of these dots. It has to be done according to specification. And if you failed somewhere, the chip can be thrown away. And how are you going to design a complex chip like this? The modeling cannot model something that large in size, and experimental help is not really there because it's very hard to make these experiments. They're very expensive. You need to manufacture something, you need to verify it. You made a mistake, you have to redo it. It's very, very expensive. So you gain a lot in terms of speed. Obviously, processing with light waves is very fast, but you lose a lot in almost every other aspect. And that's why you see a lot of high end publications where they say a single operator, they implement it with optics, and they say, okay, here's the modeling, here's the experiment. Everything works great. That's a great alternative to CMOS. And that's it. It doesn't really go beyond the article. And I think magnetics offers us some opportunities that are unique to the field. You cannot really realize them in optics, but in magnetics they are exceptionally simple, and we learned in the past few decades how to harness them. First and foremost, we can create an arbitrary shaped magnetic field by using recording media. We record some pattern there, and this pattern generates the bias field. And for the recording media, we can use either something that is based on magnetic dots, so BPM, and in which case each dot, well, let's say it's 10 or maybe 15 nanometers in size, 15 by 15 nanometers, something like this. It has a specific magnetization dipole pointing up or down, and you have an array of such dipoles. In a recording media that is used currently in hard drives, of course, you have grains, and the cluster of grains will correspond also to a stable magnetic dipole pointing up or down. This will generate an arbitrary field in another layer which we put next to it, which is a propagation layer. And that's a layer made from some soft material. And that's where I'm going to run spin waves. And what happens is, as this spin wave travels through the material, which is subject to the bias field produced by the bias layer, by the recording layer, is going to scatter. And it's going to scatter exactly as we force it by the magnetization pattern. And it's going to perform a computation that we want. And this kind of flexibility to use a re-recordable media to define the bias field, to define the propagation properties for a wave, is not really readily available in optics or in any other field of physics. But in magnetics, it's done very, very, very simple. Best material for the propagation layer, something with low damping, low MS, low HK. YIG or permalloy will do fine. Best material for the bias layer, something with high HK, high MS. Very similar to the current media, probably multi-layer of different materials to get the best combination of properties. But the details can be worked out. The simplest way you can do with a technology like this is to create a frequency-dependent pattern, mode pattern, that corresponds to a specific pattern that you encode onto the bias layer. So with YIG, which is very low MS material, you can actually use the bias layer, the dot pattern in the bias layer. We denote by color, white or black, the different directions of magnetization. So most are pointing up, but some are in black, are reversed and pointing down. So we can use a pattern like this to define how spin waves are going to travel in the system. For example, here we have 3 bridges, you might say, of different widths joined together. My apologies. And where the wide segments of the bridge coincide, you get a low frequency path. And where you have narrow segments of the bridge, you get high frequency paths. And that can be used for guidance of spin waves in the sample. You can do something far more flexible. You can actually use a bias pattern, which is a orientation-dependent wave vector, orientation-dependent grating, to say I want my spin wave mode to rotate like this depending on the frequency. And that's very easy to do. You apply a RF field in one point, and your other peak amplitude rotates on the curve just like that. And that can be used for Fourier decomposition. It could be used some guidance, spin wave guidance, if you want to move them from one area to another. A very, very simple technology, but now we are going to talk about operators, summations, logic, multiplications. I have to admit, this page, a lot of people actually asked me to remove it, but I chose it because I want to show that I'm a little bit of a real physicist. I can write some weird crap on the board, and people maybe will think that I'm very smart from this. Basically, we can implement a lot of math just using perturbation theory. The system where the propagation layer is saturated by some external field, and the magnetization pattern acts as a perturbation term. And then the first order term can be used, for example, for summations. And second order perturbation term we can use for multiplication. And these perturbation matrices that go into the perturbation term will correspond to specific magnetization patterns. So we take 2 magnetization patterns, and each acts as an operator, and the result of some observation of the amplitude of a spin wave in some area will be the multiplication of these two operators. And we're actually going to demonstrate it starting right here. This is a very small sample of dot pattern, which is 12 by 12 nanometers with 12 nanometer interdot spacing on top of the permalloy propagation layer. It's all very small because it's very easy to numerically model something like this, but we are going to show some elements that are microns in size, and they're modeled using different technique. But this one is very, very typical standard FDTD kind of a modeling. So here you have two input fields, and this is input field 1, input field 2, and inside those input fields you put some patterns, mixization patterns. So most of the dots are parallel to the external field, they're pointing up. Some dots which are in black have been reversed, their mixization points down. And these patterns in the input areas, they correspond to different input values. So if nothing would be here, there would be all the dots would be white, they would be uniform magnetized. Then these two inputs will produce the output, which is measured as amplitude over here, corresponding to the sum of the corresponding values. So if both encode once, you get the amplitude, which is a factor of 2, and both are encoding the values of 2, you get the twice the amplitude, which is kind of the factor of 4. And if you look at the modeling results, they're very, very similar to what we want. Now we want to add to this a multiplication operator, which corresponds to the second order perturbation in the expression. And we continue to measure the amplitude in this area to see what kind of output we have. And on the next page, I will show some modes and how it actually looks like. And again, you can see that we are trying to encode this kind of multiplication. So the second field, the value in the second field gets multiplied by additional factor of 2. And you see that again, the multiplication and the modeled values are very, very similar. It has to be noted that, of course, when you measure some amplitude output, you use normalization. You deal with normalized values rather than with the absolute amplitudes, but you want the relationship of these cases to all be just like you want it. Logic elements. And logic elements are a little bit harder to find patterns that correspond to them, and this is discussed in the papers because typically you use the same kind of formulation you borrow from optical computing, where our logical elements is phase inverter and beam combiner. So if you have 100 elements, you want to do AND, you can basically invert phase of every second element and try to sum them. And that's a good example. This is an operator AND encoded here for two input values. And it operates in a way that if the values in both input fields are the same, you get low amplitude output. If they're different, you get high amplitude output. So the examples of the amplitudes measured are over here, and you can see that actually the modes are clearly very different. So in this case, which corresponds to the 2-1 different inputs, you see a lot of amplitude in the output area. In these cases, you can barely see anything in the output area. So very simple measurement. Another algorithm that is quite easy to implement is quantum Grover search. That was initially proposed for quantum computing, but there were optics-based implementations as well. And basically, it's a search which goes as n, where n is the number of elements stored, and allows you to find a certain element in a pattern of elements and report what's the location of this element. Now, with spin waves, you can actually implement something more complex, where you not only it goes as a factor of n, it finds all the elements you are searching for at the same time. So you have some location for the inputs, and then you have this Grover search operator, which will transmit into the output area, the spin wave mode, with the peaks that correspond to the locations of number 2. So this is the pattern that encodes number 2, and these are the patterns that encode number 1. So in the first case, you have no 2's here, and your output area is completely dull and uneventful. In this case, you have the value of 2 encoded by these 2 patterns, and corresponding output area, you have maximums in the 2 areas. And you can actually calculate what's this questioning pattern corresponding to the value of 2, to the value of 1, to the value of 3, and so on and so on and so on, where each of these values correspond to a specific input pattern. Now, I concentrating a lot on inputs that are entered as patterns for many reasons, because it shows that the inputs which are data and the inputs which are algorithms essentially the same. So these patterns, they give you some input values, but also by themselves they perform an addition. So they can do both things, act as an operator and act as a data. Our computer does not distinguish data from algorithms in many ways. Also, that conventionally in spin wave computing, you use inputs that are different RF fields, and they're somehow synchronized. And that's something that can be done in the lab, can be done for a single operator, but it's very difficult to do if you have 10,000 inputs. And also you have to understand that if your entire RF amplitude comes from the inputs and there are no RF field applied to all other segments of the system, then these spin waves will die out as 1 over r, where r is the distance to your input areas. And therefore, the power that you will lose from this kind of setup is tremendous. So it's much more effective to create a system where the inputs are not RF fields, where RF field is just kind of a power supply that you apply to the entire sample, and you implement it as magnetization patterns, for example. Now, the problem with magnetization patterns is that you need to update them somehow, and that's not trivial. And of course, you can use STRAM like elements, but that's, again, very expensive, and we are shooting for something that is as cheap as possible. And it turns out that you can use static DC magnetic fields as inputs. The reason is that spin wave amplitude changes if you apply external field, obviously. This external field does not have to be produced by a magnetization pattern. It can be produced by a wire. And there are ways to actually implement very complex data points and algorithms using a combination of wires. And that's also allows for very fast update. All you do is just change the amplitude of current you pass through a specific wire. So here is an example of a very simplistic implementation where you have 9 inputs. Each one is encoded by 2 wires. These wires, the parameters of the wires are given here. There's a current that passes through the wires, and to a specific amplitude of currents, we correspond specific input values. And then there's a bias pattern in the bias layer on top of it, which is implementing a summation, weighted summation where weights are going as square roots of the input channel numbers. So the weight over here is 1, the weight over here is 3. And that's very simple to see that, yeah, you can model something like this. And whether you want to have the amplitude of 6, you get relatively large excitation in the output area. Where your output is supposed to be 1.5, you get substantially small excitation in the output area. So the input with wires work. And that's something that makes this kind of device much more practical. By comparison, if you look at a typical spin wave computer that is proposed in academic papers, it uses not magnetization pattern that you set as you want yourself, but a vortex or domain vault to do spin wave control. And that, of course, does not have the flexibility, does not have the simplicity, does not have the size of an arbitrary recorded magnetization pattern. It can do very little to control a specific mode. versus the pattern which you want. You will make the pattern you want, and it will do what you want. You are not limited by how vertex is supposed to look like. And it's very easy to create, it's very stable. And also, the inputs are now your DC fields. That's the simplest way you can possibly provide an input to any system. So, another very important component today of many AI algorithms is probabilistic summation. So you have a neural network that doesn't just do a weight summation of data from the previous layer of neurons, but the weights themselves, they have some probabilistic distribution. Well, it's very easy to enact something like this with a magnetization pattern. You hit it with a thermal profile, and it can be either very hot wire or it can be a laser pulse. The durations, if you're talking about temperatures close to TC, the durations you need are really 10, 20 nanoseconds, something like this. And then the system will be very quickly equilibrating to a set of possible states which correspond to different arrangements of the magnetizations in the affected area. And each arrangement of magnetizations will correspond to specific changes in your algorithm. So you can make weighted average that uses probabilistic distribution for the weights, and this probability is actually physical. It's not a pseudo-random generator. That's something that corresponds to a specific physical phenomenon. Now, there are a couple of limitations. Limitation number one, your optical size, your spot size has to be comparable to the wavelengths, spin wave wavelengths you use for computing. So that can be anywhere between 50 to 500 millimeters. The other thing is that, unfortunately, it's very hard to target just one of the weights. So you typically view, if you, for example, have a few inputs and you want to target one input, the weight for one input, you usually will affect the inputs for the weights for the neighboring inputs. That's not critical in neuromorphic computing, because in neuromorphic computing, the weights for neighboring synapses are supposed to be correlated, so it can be actually a good thing, but it's something you have to keep in mind. And that's a very typical example. You apply thermal profile for 25 nanoseconds at this location, and that's exactly the 9 inputs from the previous system. And you see that the weight for the input 4 in the system we discussed on the previous page was the square root of 4, so 2. And that's the kind of default value you get without any temperature. And actually also the most probable value. That's the way the system's set up in this particular case. But you also get a lot of different possibilities. And they, of course, will depend on how hot is your temperature profile, what are the media parameters over there, how you arrange your algorithm, and so on and so on and so on. So you can get different probability distributions of the weights. And this is obviously probably not the most clear case. You maybe want something more Gaussian looking, and there's a way to do that. The key question, so how fast it is, and what can be said about speed, let's say, if you have not just one element, but thousands and thousands of them. And it's relatively easy to compute. You put, for example, for weighted summation, you put a lot of add operators, and then you put a multiplier that's weighted summation. You change one of the operators, and then you wait until your output approaches your final value, your final result within 99% precision. Now, there are two times that enter into this calculation time. So there's a total convergence time, which is the time when you get the correct output after you finished reversing your magnetic pattern or finished adjusting your fields, your currents if you use wires as inputs. And there's a time which actually is taken by the damping to damp out this additional magnetic energy that is inserted in the system. So the time needed for the system to equilibrate to the minimization configuration, and the time that takes for spin waves to propagate. And actually, spin wave propagation is very, very, very predictable. That's accuracy at about speed of 5 to 10 microns per nanosecond for most of the implementations given here. The damping itself is basically it's 100 to 200 nanoseconds from your execution time. So when we look at the final results, and this actually results I took from some review paper from the most advanced AI chips that are being produced today, and you can see that the time per cycle, time for a single weighted summation in neural network, it's exceptionally fast compared to current CMOS. And that's not a surprise because we use physical properties of a spin wave, of interference of spin waves to do summation. We do not make a summation out of many, many, many different transistors, and each transistor can do only a logic element essentially. And by the same token, our size is much, much, much smaller because again, we do not waste space on building a lot of elements that each they can do only logic. Now, the power comparison is difficult. And that really depends on how well can you read the output signal. If you have really bad detector, you will have to operate with high powers, obviously. If you are talking about detectors comparable to what we have in the current spin wave experiments, you can put actually a substantially small number here. So this number is a little bit speculative, but it seems that the promise of spin wave computing being low power computing that you see in every single paper on the subject, it does hold to some extent. Very important consideration, it's exceptionally cheap. All we have here is magnetic recording media and a couple of wires and RF current generator. That's all exceptionally cheap, and we don't need any lithography whatsoever to encode a specific algorithm. We do it by means of magnetic recording. So yes, this per, let's say, 25.6 neurons CMOS CPU doesn't look like horribly expensive, but you have to remember that there is also $1 billion spent in a production facility here, and this production facility will have to be updated. The mask will have to be updated for a specific CPU to be done. The manufacturing cycle has nothing comparable. Here we just record the pattern. Here we have to lithographically redefine the entire set of your operating devices with nanometer precision. So a lot of advantages, and the whole technology is exceptionally cheap. I did go a little bit further and analyzed what happens in terms of data resolution, result precision for, again, a simple 256 neuron chip. So there's a weighted summation of 256 input elements. And I used different media parameters. I used different media parameters for bias material, different media parameters for propagation material. And it turns out that, of course, the most expensive combination, which is YIG with a bias material, which is iron cobalt BPM, is exceptionally good in terms of data resolution and in terms of precision of the result. But it's also something that is not readily available off the shelf right now. SUL, again, that kind of matches to some extent the setup being proposed, that you have a soft layer underneath magnetic recording media. Unfortunately, what we know about SUL, or let's say what we suspect to know about SUL, about its roughness, about the large distance it has to the recording layer. Not too exciting sometimes. So, but it still can still work. And maybe there's an experiment that can be done or something like this. But it's probably some of the worst combinations that is out there. Now, permalloy actually, again, if you're not entering some extra surface roughness there, you do not penalize the material somehow, that actually performs quite decently. These numbers are well within the parameters that you see in the specialized chips today, and actually better than some of the specialized chips today. So what do you do for RF excitation? I think in terms of a chip-based implementation, this is something that is RF current source plus a wire. That's something that we know how to make, we know how to integrate, and here we don't have to somehow make it a very thin wire. We don't really have a lot of restrictions or something like this. And the typical operating frequency is anywhere between 5 and 40 gigahertz. Now, it can be extended further up in the future, but it will require a very different set of materials and a very different problem. For detection, ideally in the device, the actual device you manufacture, you would use magnetic reader, I think. From my modeling, it's more than capable of detecting spin waves, but it's never been used in this capacity. Basically, in the lab, you want something that is removable, that is not integrated in the material, so you use the meander with the beta network analyzer, or you use something like BLS. That gives you even some spatial resolution. You can monitor your spin wave mode in different sections of material. So, really, a lot of possibilities. We can use in the lab something like this for the experimental verification. And in the actual device, something like this can be envisioned as well. So there have been a lot of skepticism, quite honestly. The first time I submitted an article, the article that was the first in the series, it's received a lot of very negative reviews. I had to essentially cut it down in scope and expand it in explanation. And a lot of these reviews will say, well, this will never work because there are imperfections in the media, in the dots. Well, they do matter if their size is comparable to wavelengths you use for computing. So if it's not, and it's obviously not, then you don't care that much. Ambient temperature, again, it doesn't contain a wavelengths that is somehow interferes with this computing. It's a kind of a broadband noise that does impact your readout SNR, but shouldn't impact significantly your computational performance. Now, linear effects, a very interesting subject, and there's a possibility to make a computing scheme based on a linear interaction between magnons. I don't want to deal with this yet because there's a lot on my plate, to be honest, with this. Spin wave amplification. So, can you do spin wave amplification? This kind of setup, and the answer is yes, you can. Unfortunately, it will be a complex subject of its own, and right now we just satisfied with driving the entire surface of the chip with RF field. That really prevents from a lot of spin wave power losses you do observe in experiments where you use RF fields as inputs, and that should be sufficient to make relatively large chips. So problems and unknowns, and this is just a couple of honest and not so honest admissions. The modeling presented here is politely very edge of usability and believability. So I've seen my share of modeling failures in magnetics, and these systems are hard to model. Spin waves overall quite hard to model. I think in principle it works, and I'm working on modeling techniques that will have greatly improved precision and hopefully will be even faster for these specific tasks. But overall, this is very complex modeling, and while the principle I think is solid, modeling is difficult to do. Um, a lot of things we need to get from experiments. So modeling is nice, but the experiment will tell us what to expect and what to observe, and whether it works or not. It also will depend largely on the experiment. And that's what makes me a little bit depressed, is that even if everything comes out fine, I think that this field, we do know the basic physics very well, and we do know that the impact should be observed, and probably the system will behave more or less as predicted. It doesn't immediately mean it will be commercially available, great success, but the effect, the phenomena is there. The problem is, to make it a commercial success, you essentially need to develop a completely new programming language. Because now your precision depends on physical distance between operators. You do not gain anything from doing bit by bit logic operators. If you do logic, you really can do it on a huge array, and that will not cost you much more than if you do it with two elements. The same can be said about a lot of different operations. They are so parallel by nature. This spin wave interference is so parallelizable by nature that you really need to have a programming language that keeps it in mind. And you give it kind of a task to implement, and then it thinks about which operators are the best to do that, and then it thinks about how to combine the magnetic patterns in the recording media in the best way to ensure that these are the operators implemented. That's it. Thank you very much, and I hope that this presentation was at least somewhat interesting. Thank you. Goodbye.